Welcome back to High Performance Computing, Advanced Scientific Computing course, lecture 13. We will carry on this lecture about the transformer application in fluid dynamics. In first part, we talk about the attention mechanism and how its structure working. There was different architecture of the attention mechanism and we present some difference between two the main types of the attention mechanism. Here we will talk about the transformers and its feature, and we'll present its application. The transformer architectures, as you can see here in this figure, it's composed of two main parts, encoder and decoder. Number of the encoder and decoder must be equal, and we will look on this feature on the main paper of the transformer when it's born and how they applied it on the translation. And you can see here is the example of the vision transformer architecture and how the image is split into 9 patches. And how the transformer with encoder and decoder made the label for these uh, patches of the image. When the transformer it's born, it came from the paper Attention is All You Need, uh, which explain the transformer base of this paper. Transformer is the deep learning network composed of encoder and decoder architecture. The input data feed the encoder layers and generate the output via the decoder. The mechanism of this process has several steps. The number of encoder layers must be equal to the decoder layer. So this is important point regarding the transformer. In order to specify the input sequence and distance, positional embedding is added to the input vectors. The positional embedded input vectors feed the first encoding layer, and the output of the previous encoder layer provides the successive layers. Every encoder layer is broken down into two sub-layers. The first encoder inputs stream through a multi-head attention sublayer. In a multi-head sublayer, all inputs dependencies are considered to create the weight matrix. The next step is the outputs from the multi-head sublayer stream to the feed-forward sublayer. Between these sublayers, there is an add and norm intermediate sublayer, which adds the inputs of the multi-head sublayer to its input and normalize them. So we are going step by step how the transformer map flow is working. In the feed forward sublayer, the data is independently applied to each position. Thus, in the feed forward sublayer, data can process in parallel and independently. The outputs from the feed forward sublayer in the same manner should pass the add and norm intermediate sublayer. Consequently, the data has been processed into an encoder layer, then flowed into the next encoder layer. The number of the encoder layers have no specific and magic number. This point when you want design transformer model, it's difficult part to specify the number of the layers, and they must be resolved and determined in the architecture design for every problem. When the first transformer architecture was born, it was designed with only 6 encoder-decoder layers with notable achievement. This feature of the transformer architecture mentions a remarkable capability to model sequential data problem with fewer layers. Reducing the number of layers in deep learning model could lead to less computing than other sequential models such as LSTM and GAUSS. So you can see here the map flow of the transformer here we presented it in sequence with the main feature. Regarding the parallelization on the transformer, indeed it has a good capability to apply in the parallelization. As you can see here in this paper from their application, they said a new simple network architecture, the transformer, based solely on attention mechanism, dispensing with recurrence and convolutions entirely. Experiment on two machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. So this point regarding the transformer, it's displays transformer has a good parallelization feature. Then we can reduce the computing cost, and on the other hand, we have many examples that the prediction and the accuracy of the prediction of the transformer is remarkable. And with parallelization, we can have better and faster solution. Let's have a physical example. In our recent study, we applied the transformer model for turbulent flow data, which this case of the turbulence flow, it's in the specific condition. These data extracted from experiment, which flow with a specific Reynolds number, and it's underwent to the deformation, and with a technique of particle tracking velocimetry or Lagrangian particle tracking, the velocity location of the particle recorded and processed. Then we have a time series of the data with particle motion. That means we have sequence data presenting the velocity of every single particle during a specific time. From the dataset information, here I can explain that the data has a 2,862,119 tracking point for every vector, and every vector has a component velocity in y direction and velocity component in x direction, and the time vector which specifies the time for every tracking point. We applied this data to make prediction. We have sequential data from the velocity with a specific period. So we use part of the data for training with velocity, and then looking for the prediction of the velocity in next time step. To do that, we split the data to a specific ratio of the training and the validation data, 80% training, 20% validation, and second time 60% training and 40% test data. This is the short description of the data. This work on the paper, and of course, detail is available from this work. And in the references, you can look on this paper with detail. If we want to look on the data about the velocity, as I said, we have the velocity in y direction. Here, the velocity values during a specific time, as you can see how many data. This presenting the velocity in y direction, and this one velocity in the x direction. So when we say we're using 60%, like we're using 60% of this data for training and the rest of the data for the validation or test data. Regarding the architecture of the transformer model we used, we designed the transformer with four encoder layers and then equal decoder layers. As we said, they must be equal. And of course, with the sequence of the transformer, which is well known from the original paper. Um, and we use this optimized number of a layer, which is provide a really good resultant capability of its prediction. Now let's have a practical example from this transformer. As I told you, this model is used on the physical data. We can try to run this simulation. If we look on the data, this is the data. We have time, location x and y, and velocity in the y direction. And this time series of the data. Here in this data, in this file, we have 219,000 data. This is not all the data that I presented in the previous one, because the main data is with 2 million data. Here we reduce it to be able to run it with shorter time. Regarding the code, here we have the transformer code on the Python. Here is the code. We import the required libraries, and we are using, then here we're reading the data, and we create the time series with the data, doing the normalization, and we using the Windows method to make the sequence data. Regarding the training data here, it's set up with 80% training. We can make it, for example, 60% training and 40% for validation. And here the model is created, the function to create the model, the normalization and the attention part, which is create the encoder and decoder layers. And then here we running the model. As you can see, with this number of epoch, however, we can change the epoch. About the batch size as well, we can change them. When we run this code, we can see the result. Let's run these transformer model. Here we are using the deep machine on the Julius Computer Center. We will submit the batch file. There is the setup for the batch file. You can use this setup, of course, for your assignment, which you are using some other model on the LSTM or Go. As you can see, the name of the project, we're using the partition DPESP, name of the this job, and number of the node, number of the GPUs, and here the required module, and here the command to run the Python code. Everything here is ready to submit the job. Only we need to write a batch script sh. As you can see, the work is submitted. To see the list of the submitted work, we can use this command -u, and this is the user count. As you can see, this is some information from previous job submitted, and here for the last job we submitted, this is the number. Uh, last 3D 460, 400, it's here, it's submitted with 8 nodes, and it's pending now. If you want to look on the detail of the work, we can write control R, the number of the work. There is a detail of this work that submitted the job. It's pending, and of course, when it's running, we expected to see the result. Since this is the architecture of the transformer model here. However, this training is taking time to be finished. Regarding this submission, when we obtain the result, here you can see the prediction of the transformer when we made the training with 80% for the velocity in y direction. This is the prediction. This green color, it's the prediction, and the red one is the actual data. You see how much is matching with the real data. This is the y direction. When we make prediction with 60% and 40% test data, also here we can see how much the prediction match with the actual data in the y direction, x direction. So it's mean the capability of the transformer to make prediction. It's really in a good level, and however, about the computing time in this application, the size of the data was not too large. So about the parallelization to see how the GPUs could be accelerate the application, we have not tried it because the data was not too large, but it's planned the future with larger data. We can see how the GPU helping to accelerate the training on the transformer as well. So here we have example of this application, which is presenting the capability of the transformer in the fluid dynamic area. The result of this application for 2D turbulent flow, it has some physical feature which impact the flow behavior, like the turbulence intensity, strain rate, and gravity effect. But we did not use these effects for training, and they did not has a direct training on the model, but only with the velocity, time series velocity, and position of every single particle. We were able to have these simulation and prediction of the following period of the fluid. This design relies on the concept that velocity carries and transfers the most important flow features. The model is independent of the velocity component and trained and predict each velocity component individually. As you saw in the result, we have prediction for the velocity in x and y direction individually. The transformer was trained with two portions of training data, 80% and 60%. The error measurement illustrates the mean absolute error and R2 score in a range of 0.002 to 0.003 and 0.98 respectively, which is a considerable prediction and almost matches the actual data. Of course, in the deep learning, the capability of transform model, it seems, can make a simulation and prediction with less data, which is good capability. With less data, the computation it will be cheaper. And however, because the number of the layer in the transformer, it seems going to be less than the other sequential model like LSTM or GRU, it also will reduce the computing. Here we finished the second part of this lecture 13 about the transformer and its application in the fluid dynamics area. And we had a review on the architecture of the transformer, which is one of the recent deep learning capability for sequential data. And from the practical example we had, it seems there is a good perspective for the future application of this model in the physical use cases. In the last slide, there is a video which is explaining the transformers with visualization, and it has a good example, and I suggest you watch this video. Thank you, and here there are the references for this lecture. You can have more detail about these transformer model that we presented it. It's from the experiment. And see you in the next lecture. Thank you.